As they make their epic journeys across the continents, railways continue to push boundaries ever further. Inspiring engineers to find new ways to tackle all of nature's extremes. But there is one challenge that raises the bar higher than any other. The mighty peaks and sheer cliffs of mountains. From their treacherous, winding terrain,
Semmering features grades and curves that has never conquered before by a railroad.
to impossible inclines for trains.
The steeper you make it, the bigger the train you need in order to overcome this incline.
And passengers to overcome.
The challenge here is because the natural wall is more or less vertical, so we have to find a way.
It was the challenge of one epic climb that faced Swiss engineers in the mid-1800s. Inclines are often a test for trains. But the struggle to overcome them is always worth it. The trouble is, when they do make it to the top, of course what goes up still has to come back down. The Swiss Alps, part of the largest mountain range in Europe, and home to some of its highest peaks. For centuries, their alpine vistas have been attracting tourists with a sense of adventure. But with their unrelentingly steep terrain, these mighty mountains are a railway's most formidable opponent. Railway technician Stefan Reichel is travelling on the Rigi railway to see how adaptations to the track and the engine made it one of the first railways to take on a seemingly impossible mountain climb.
Look at that sunshine. Look at this Rigi mountains. I love it. And now you can hear the engine starts working hard because it's very steep on Rigi. And now listen to that noise. The fireman is doing his work. He needs to shovel 500 kilograms of coal into the boiler up to Rigi Staffel.
Today, this train is one of the most popular tourist trains in Switzerland. But in the early 1800s, the only way to reach the vertiginous heights of Mount Rigi was on foot or by carriage. In 1869, engineer and locomotive builder Niklaus Riggenbach was commissioned to connect Witznau on the shores of Lake Luzerne with the summit of Mount Rigi, 1,798 meters above sea level.
What Riggenbach really found was just working up here was hard.
Having seen trains slipping and losing traction on other railways with shallower gradients, Riggenbach knew his solution would require radical rethinking. The railway would have to climb 1,115 meters in just 5 kilometers.
Now we are at the steep gradient, the boulder is now in level, and the engine couldn't hold on by pure adhesion. So it has to grab to something. Like children would slide down a slide, the engine would slide down here if it's pure adhesion. So if children go backwards to slide, they grab onto something. And Riggenbach did the same. He used something where the engine could hold on, or could grab on. So he invented a third rail between the normal rails.
Riggenbach designed a toothed rack rail between the running rails. A cogwheel was added to the center of the wheel axle to mesh with this rack rail and give the train traction.
And this is how the cogwheels inside merge into the third rail of the rack system. And this is how the engine gets a hold.
In 1871, the Rigi Railway was the first rack and pinion railway in Europe to conquer a mountain.
And now listen to that noise. This is why you sit directly behind the engine because you have to enjoy a working engine. And you can feel the engine moving by that rattling and by now speeding up. This is only about 6 miles per hour, but it sounds like we're going 100 miles, and it's nearly you're going up. It's like Riggenbach built a stairway to heaven.
Taking nearly 2 years to complete, Riggenbach had finally brought this mountain to the masses. And today, as many as 500,000 people a year make the journey to the summit.
Up here, this is one of the best views I ever have seen in my whole life. I have been to many mountaintops, but none of that had that panorama as Rigi. Now I know why Riggenbach conquered the mountain with that tiny railroad, but up here it's only half of the problem.
Having managed to get the tourists to the top of the mountain, the elevated incline presented Riggenbach with a challenge of equally tough proportions. With a 25% gradient, the rate of descent was creating too much stress on the boiler and band brakes of his locomotive, as well as damaging the track.
Usually on an incline, the most railways encountered a very problem because the wear on the brakes was so high that the brakes could fail. And so you roll down without any brakes and could derail, and many accidents happen.
For a train full of passengers, this could have been catastrophic. Riggenbach needed to find a way to slow the train down.
Rigi was too steep for normal braking systems, and so he decided to use a different brake system, a brake system which could not fall apart.
Riggenbach surmised that if the engine was strong enough to push the locomotive and carriages up the mountain, then it should be strong enough to slow it down on its descent.
And now we go down by Riggenbach. And this is what Riggenbach really invented. There's the brake system. What we hear right now is air is moving into the cylinders and it's pressed out by the silencer next to the stack. Did you hear it? The chugging noise has changed. It is now a noise of compressed air.
When the engine is running, the Riggenbach air valve is switched, so that exhaust will leave by the blast pipe. To apply the brake, the throttle valve is closed and the Riggenbach air valve is switched in the opposite direction, allowing the pistons to pull clean air in. The air becomes compressed in the cylinder, acting like a cushion and slowing the pistons down, which in turn slows the train.
Personally, I think this is the best dynamic braking system for steam locomotives you ever can have, because it has no additional structural details which need to be special. You can build it in any steam locomotive of any type, and it's an absolute valuable brake system because it applies the brake pressure by itself. As faster the train goes, as harder the brake is acting.
The Rigi Railway became the highest standard gauge railway in Europe.
Being here at Rigi is something very, very special because it's the oldest operating cock rail in Europe. It's an absolute awesome ride upwards and then going down with the Riggenbach brakes, smooth, soft. That's the invention we are all for here. This is what makes the genius of Riggenbach.
The Great Mountain Railways, cutting their way through treacherous terrain to complete their incredible journeys. But every mountain range throws up unique challenges, some seemingly impossible to overcome. Given enough firepower, most ordinary trains can climb a hill. But no matter how hard you try, extra muscle can only get you so far. Huh? Ecuador. From the Pacific Ocean to the mighty Andes. It's a country full of larger-than-life landscapes that seemed unconquerable in the late 1800s.
The Andes Mountains in Ecuador run north-south for about 600 kilometers with peaks over the 5,000 meters and then actually getting down to zero level. It was very important to connect the capital city, Quito, and Guayaquil, the main port, that were geographically separated.
Although only 268 kilometers apart as the Condor flies, these two strategically important cities were separated by raging rivers, dense cloud forests, and deep ravines. The ambition was to build a railway across this terrain. But as Tren Ecuador's Alex Ortiz knows, achieving it would be no mean feat.
Guayaquil, it's in the lowlands at sea level, and Quito, it's over 2,800 meters above sea level and then getting to the Central Valley. So the engineers had this incredible task to go from the coast through the mountains, through this steep valley. It's very difficult to imagine a train going through these mountains, through these vertical walls.
For centuries, the perilous journey between the two had only been possible by mule, taking up to 12 days to complete. At the end of the 19th century, the country's leadership enlisted the help of two American brothers, John and Archer Harmon, to start work on the Trans-Andean Railway. But there was one section that was seemingly impossible to overcome. The Devil's Nose. With its precipitous drops and impenetrably hard rock face, building a track that could circumvent and ascend this section would pose one almighty engineering challenge. But inspiration lay, incredibly, in their surroundings.
So the trails that they are all around over here, the ancient trails in zigzag, like a switchback, like the ones I have on my back. They thought this could be the great solution.
In 1908, after 10 arduous years of construction, using a workforce of thousands, the first major rail network of the Republic of Ecuador was completed, finally connecting Quito and Guayaquil by rail.
This is the Devil's Nose, a historical railway, a feat of engineering. I've seen it many times and it still blows my mind. It's incredible.
Made possible only by a feat of engineering at this most imposing section of the line. This is one of the highest active narrow-gauge railways in the world. Tour guide Santiago makes this world-famous journey on a regular basis.
I never get bored of sharing this route with the world. It's pretty amazing. The landscapes, it's an amazing route.
The ingenious solution engineers turned to was a switchback, a zigzag section of track with reversing points. This enables the train to traverse this extreme gradient and gain 100 meters in altitude as it travels between two switchbacks.
So right now, we are going through the famous Devil's Nose. So we're going up through the track in reverse, 1 kilometer, gaining about 80 to 100 meters in altitude. What is important to mention about this maneuver that is pretty amazing is that the mechanism that allows to exchange the tracks are hand pulled by the brequeros, the members of the crew. Right now, the brequero leave the car, pull the switch, allowing us to go through it in reverse. Again, when we reach the end of the zigzag, there we will stop for a few seconds. The brequero will leave the unit again, pull the switch, and from there we go straight forward. You look closely to the window, you get lost in the view, and you feel like you're floating in the train through the track.
This inspired concept solved the most troublesome section of the railway. And in doing so, a journey that once took 12 days was reduced to just 14 hours.
The establishment of the track for Ecuador was something very important. The connection was better, transportation of goods, cargo, passengers, so there was a better dynamic on the communication between the two main cities, Guayaquil and Quito.
Despite flood damage in 1998, which destroyed much of the line, the Devil's Nose section never closed.
The engineering behind the Devil's Nose is outstanding. To get through these mountains was thought impossible for so long. Despite the massive challenge of building the Devil's Nose section, today, over a century of being built, is one of the most stable areas of this line. And that's the testament how great was the switchback solution. I think this is probably the most incredible railway in the world.
Finding a route that can reduce the gradient is one way to tackle a mountain. But some inclines are so extreme, their engineering is from the realms of science fiction. Some railway tracks are made for inclines. But people always want to get to the top faster. Come on! The obvious solution is building a line that's steeper still. But the steeper you go means your train might get there, but your passengers won't.
Hey!
With steep-sided mountains and Arctic winters, at 1,300 meters, the alpine village of Stoos in Switzerland is about as remote as it gets. Popular with skiers, its tiny population of about 100 dramatically swells to over 2,000 during peak season. For the village and its visitors, an aging funicular was their only connection with the valley below. But this vital public service was failing to keep up with the needs of the passengers. Senior engineer Bruno Liefert was all too aware of the increasing demands it had to meet. It had to go faster, carry more people, and be easily accessible.
Here we stand on the old Stoosbahn. This, in 1933, it was really the steepest funicular in Europe. But the track is going around the mountain with 120 degrees. And we had to find out a new track possibility with a straight track. So therefore, after 84 years in use, we had to replace it and we had to build it in parallel to the old funicular.
But to find a new route meant confronting grueling mountainous terrain.
They told me, Bruno, you're crazy. That's impossible. But I was not happy with this answer, so I challenged them and say, hey, as long as you don't say it's a no-go, we will find a solution. And now you can see the solution is built.
Stoosbahn, the greatest incline ever conquered by rail, opened to the public in December 2017.
We have done something nobody else has done before, so it's really a new area and we created a new type of funicular.
ascending a whopping 2,500 feet from the base of the mountain at a jaw-dropping angle of 48 degrees. This 21st century funicular is truly groundbreaking. With such a precipitous incline, keeping the passengers upright on the journey was the first challenge. The answer was a cutting-edge carriage.
One of the main goals of the new Stoosbahn was we make it horizontal at both stations.
Mechanical engineer Niklaus Moser was part of the design team.
The demand for easy access for the passengers is increasing, and then we have some very steep sections and flat sections which really required a leveling system, and that was achieved with the new system.
What the team came up with was a carriage with a fixed chassis and individual cylindrical cars that rotate to keep the passengers and freight horizontal at such a steep angle. It was the first of its kind in the world. Having to fit essential testing and maintenance of the carriages around a busy timetable, Niklaus and his team make the most of the 15-minute window when the train is in the station.
We now are below the train where we see best how the leveling device is done during the ride. And then you see these two cylinders on the left-hand side and the right-hand side. They are connected to the lower part of the round-shaped cabins. And once they move this way or that way, that means that the cabins are rotating around.
Inbuilt inclinometers sense the angle of the track, signaling the hydraulic cylinder system to kick in and compensate for the incline. By rotating the carriages accordingly, always keeping the floor horizontal and the passengers upright.
You don't really feel that the train is changing the gradient as you stay on the floor. You just glide up to the top station and you don't feel it.
A routine test reveals just how the mechanism works to overcome the 110% incline.
So now we are testing again, and we go to a full inclination of the train on the track would have. Respectively now here our cabins. I'm holding on strong here that I don't fall over. We're not yet there, but we're getting there. I hope my muscles are strong enough to hold on till we ever get to the very end. Oh. That's the limit. Jetzt müssen wir noch rauskommen.
High-altitude railways. Testing the limits of engineering to conquer nature's most difficult terrain. And one ambitious train that faced a series of problems is the Stoosbahn funicular. Today, project leader Bruno is heading back to the site of the Stoosbahn's most demanding engineering ordeal, building the track. Even now, the final stage of this journey is not for the faint-hearted.
The challenge here is because the natural wall is more or less vertical, so we had to find a way, and so therefore we created this tunnel with 48 degrees.
3 tunnels would be cut through solid mountain, starting with the highest, excavated using the simple drill and blast method. But with a near vertical gradient, the lower 2 tunnels would need a completely new approach.
So the steepest area is right here and the next 200 meters down. This tunnel here is 250 meters long, and 200 meters of these 250 are 110%.
The team used the raised drill technique with a specially designed drilling device. A very small pilot hole is drilled using a directional drilling tool. Once it emerges, the drill is then replaced with a rotating metal cutting tool, which is drawn upwards, creating a wider circular hole big enough for the explosives to be inserted and the tunnels to be enlarged to their final size.
That seems to be the most efficient method to create tunnels in such steepness. During the enlargement, all the rocks which came out went down because it's so steep, and the total amount was around 25,000 tons of material which we had to move.
Having managed to use it to their advantage with waste disposal, gravity still posed a significant risk for the construction team harnessed to the mountainside.
One of the biggest challenge was really here to ensure the safety for the workers, because it's so steep. When you lose, for example, a tool, and somebody else stands 10 meters below, this tool will have such an energy that is very, very dangerous. I can say now, really to summarize, we didn't have any really strong accident, and therefore we are very thankful.
At 1,738 meters long, the new track includes 580 meters of some of the steepest train tunnels in the world.
Sunday you're out in the open again, and then the next tunnel is coming, getting the same steepness, and it's really rather an amusement ride than a transport from A to B.
Two of these massive motors enable both carriages to achieve maximum speed, whatever the gradient.
Actually, we are now in the machine room, that's why it's a bit noisy. That's the bull wheel. It's actually transferring the movement from the motor to the rope, and the rope is connected then to the car. That's how the movement from the drive here, from the bull wheel, is transmitted to the car. Imagine 36 kilometers an hour at 50 degrees inclination. That's a big speed. It's the fastest in the world, on an inclination like 110%.
Accomplishing all the demands it set out to achieve, the Stoosbahn can carry 1,500 people every hour on the steepest railway in the world.
Travel speed is about 2.5 times as much as the old funicular was. The cars are bigger. This means that we have drastically increased transport capacity.
Every day, the brilliant engineers of this futuristic funicular keep the villagers and their visitors connected.
All the time when I see the train is passing here, it's a great feeling. It's in a way undescribable. After 14 years hard work, I'm so proud to see how the train goes up and the baby's really born and it works.
But for other railways around the world, a climb doesn't have to be steep to be an enormous engineering challenge. Birmingham, a city in the Midlands of Britain, and one that in the 18th century was striving to be at the heart of industry. But without a railway connecting the city to a major port, it was yet to become a reality. Civil engineer Fraser Godfrey is at a site on the outskirts of the city that would see engineering opinions divided.
Birmingham, by the late 16th century, was a centre of manufacturing. So growing in its industry, it was very keen to connect to Bristol in order to facilitate that transportation of goods, possibly around the world.
At that time, the port town of Liverpool had direct trade with America and was thriving. Bristol and Birmingham dreamt of a link that would allow them to compete with these big coastal cities and boost their economy.
In the 18th century, the only way to get from Birmingham to Bristol was via canal, and that was a 6-day journey. So really, railways became an obvious choice to use to distribute their goods around the country.
But there was one major obstacle for engineers to overcome.
Birmingham, as we can see quite clearly here, is on a plateau, and it is about 70 metres higher than the surrounding area.
Along the southwestern edge of the plateau are two parallel ranges of hills with a valley in between, known as the Lickey Hills.
Hills are a great engineering challenge. How do you overcome a hill?
Determined to conquer the incline, the rail company called upon some of the world's best engineers, including Isambard Kingdom Brunel.
His approach was to take a different route to enable a much shallower gradient, about 1 in 300.
But Brunel's proposed route would take the railway 5 kilometres further east, making it longer and more costly to build. Instead, beating him to the contract, Captain William Morsum came up with a much bolder solution.
He decided on this route straight up the side of the Lickey Hills, which formed the Lickey Incline.
A 3.2 kilometre stretch with a gradient of 10 degrees, around 10 times steeper than heavy trains of the time could negotiate. And the only way to overcome the gradient would be to use an additional engine, designed to push each train up the incline, by giving an extra boost of power, an ingenious system known as banking, and one that they still use today. Engine driver Richard Higgins is taking to the line to bank a freight train.
We're now departing to go to Bromsgrove via New Street. The train we're due to bank should already be here because we've been put down into the platform. We're just coming into the station now. We're going to go up beyond the train that's due to be banked. I think he weighs about 1,300 tonnes.
There are two methods of banking: buffering, which is simply pushing the train, or coupling, attaching the banking engine to the train it is assisting.
Some trains now use auto couplers for an automatic release. You press it, it releases the jaws, it lifts this up, which lifts the locking mechanism underneath, lets the jaws open, and the train will pull away from you, and you just fall back away from it. Hello, Bromsgrove, 0 Bravo 01. I'm buffered up behind 6 Zulu 46 now and ready to depart. With this train now, I just have to push it up the bank. If it's got the auto coupler on, you set the auto coupler up and you couple up to the train and you use this control here, the master switch, and that's your remote uncoupler. And now when you do that, the train in front will just pull away from you when it's reached the crown and you start to drop away. Right, we're going.
Today's more powerful locomotives are able to cope with the incline. But the principle of banking is still needed for trains heavier than 1,200 tonnes or those with a low coupling strength.
A lot of the freight trains will come up here. The majority of them do need banking. It's an important job for us because otherwise they'd have to be diverted and they go a long way round, which is not very economical fuel-wise.
It's the maximum horsepower of 3,300 that these mighty banking engines provide that make it possible to push 1,000-ton trains up the incline.
Right, we've just come off that. This is the top of the incline, a place called Blackwell. We've just come off a train now because he can carry on his own from here.
And this is still the main rail link between Birmingham and Bristol, made possible by the steepest sustained mainline railway incline in Great Britain.
So as a piece of civil engineering, the Lickey Incline is really quite basic. It's a railway up the side of a hill. But as a piece of mechanical engineering, this challenge forced engineers to develop more and more powerful locomotives, which helped with the development of locomotives, ultimately across the world.
Mountain railways, overcoming mighty peaks to connect some of the most remote destinations. But some railways are renowned the world over for their heritage. Going up one mountain is straightforward enough. But when you have to go through a whole range of them, There's a challenge around every corner, and every corner is a challenge.
Oh, come on!
The Alps, Europe's highest and widest mountain range. Covering 1,200 kilometers of forbidding peaks and valleys. This impenetrable landscape should put the brakes on any plan to build a railway. But in the heart of Austria's alpine country,
Ja, wir fahren hinten auf den ersten Plattform. Ja.
Operation Manager Klaus Bernesch is taking to the tracks to see how a seemingly impossible line through the mountains became a reality.
Riding on the locomotive is an experience because you feel the power of the steam being freed into the pistons, work there, and do propulsion to the train. It's almost a living animal.
Today, trains like this one carry tourists. But in the golden age of steam, they played a vital role in trade across the mighty Austro-Hungarian Empire. The steep peaks of Austria's Semmering Pass, though, made plotting a route for the trains to travel here an engineer's worst nightmare.
Looking back to the 19th century, the main part of Austria in the town of Trieste was blocked by mountains to Vienna. So a railway line had to build across the mountains of Semmering.
895 meters above sea level, the steep gradients and tight curves the line would need to navigate left many convinced it simply couldn't be done. But one man thought otherwise. In 1848, engineer Karl Ritter von Geiger decided he could defy the odds.
I think people thought Geiger was a little crazy, trying to operate a new railroad line. But today it's the same. How do some people think about NASA's ideas to travel to Mars?
His solution to overcoming the perilous pass was the game-changing Semmering Railway. The first mountain railway ever built. Its 41 kilometers of looping tracks carve a path through the landscape, with 15 tunnels and 15 viaducts.
The Semmering Railway is the first railway line in the world to become UNESCO World Heritage, and so is very famous all over the world.
Heritage rail expert Kirsten Ogris has come to Kalterinne, where the monumental scale of the task which faced Geiger is still clear to see today.
We see here the Kalterinne Viaduct, one of the most important viaducts of the Semmering Railway.
Standing 46 meters high and curving 189 meters across the valley. Its rows of towering arches are a testament to the treacherous terrain the line needed to cross.
A big challenge was these viaducts have narrow curves, and this in combination with the gradients, it's very difficult to build it. And they use such ordinary simple tools. They take the stone chisel and an ordinary hammer and also this iron to split the stones. It was very amazing when you think about that these big viaducts only made by hand.
But deep ravines weren't the only obstacle Geiger had to overcome. The route he chose meant trains had to climb a precipitous 457 meters height difference, an impossible feat for existing locomotives of the time.
Semmering features grades, curves, and mountainous terrain that has never conquered before by a railroad in Europe. At first, Geiger took a regular engine and made trials on a test track that had a steeping gradient, and he found out that a regular engine can operate over the gradient. It's because of the very low friction between steel wheels on steel rails.
Negotiating both gradient and tight curves called for a brand new, bespoke loco and some inspired thinking from Geiger.
He started the Semmering competition, where several manufacturers of engines could provide their ideas how to conquer the steep grades. The contestants managed to cover the already finished section of the line, but no model was suitable for a long-time operation at reasonable costs.
Instead, it was one of the contest judges, engineer Wilhelm Freiherr von Engert, who solved the conundrum.
After the competition was held, Engert found out that there are several good ideas that could be useful, and he implemented those ideas into his design, altered it a little, and a useful engine was the result.
Although built around 60 years after Engert's engine, this MH-class locomotive shares the innovations which made it so groundbreaking.
When you approach the engine from the front, you find a regular gearbox, the cylinders underneath the smokestack. It becomes very special when we reach the point where the engine connects to the tender. Normally, a tender is a regular coach filled with water and fuel.
Unlike traditional trains where the tender is a separate wagon, Engert's idea was to build an engine and a tender on an articulated frame.
You see here the end of the locomotive and the beginning of the tender floor. And putting the tender frame outside, up to this point, you provide a bigger space for a larger firebox and thus the capability of producing enough steam to go uphill for a long time.
The extra weight of part of the engine on the driving wheels of the tender helped increase the traction on the rails. Engert's solution also helped solve the problem of navigating the snaking sections of curved track.
Imagine going through this tight curve with a locomotive that is very long and has a rigid axle base. Like a straight line, if you draw the straight line, once you will reach the other rail and you will be squeezed between the rails and not able to move forward or backward. Engert solved this by putting a pivot point in the middle of the locomotive, so it's bendy. As an example, you have the pivot point and the floor of the engine, the floor of the tender, as seen from above, and the tender can move freely towards the side using the pivot point.
In 1853, Engert's locomotives successfully traversed the entire 41-kilometer length of the Semmering line, finally connecting Vienna with the sea and completing Karl Ritter von Geiger's railway through the Alps.
Geiger was very intelligent and a great visionary. And of course he had the courage to do this, to realize this project. So he was perhaps crazy.
Since the invention of the railway, mountains have been their major adversary. Inspiring remarkable creations.
It was the highest mountain they pass by railway, so it was a big challenge for the engineer and also for the human.
Elevating engineering to new heights.
It's absolute genius with marvelous machines and engineering of the whole mountain rail system.
To create impossible railways.
It's really a great experience to see it running. I think it's an amazing engineering achievement, pretty special. Yeah.